Hi students, very good morning. In today's class, we are going to discuss electric flux. So in the previous classes, you have learned what is electric field, field strength, SI unit of it, etc. Field lines also. So today we are going to see another important phenomenon related to electric field, that is electric flux. This is also another representation of electric field itself, which you have already learned. So first of all, what is flux? You know something about liquid flowing through a pipe will have volumetric flux. I mean to say consider there is a pipe through which some liquid, maybe water, is flowing, and say the cross sectional area of this pipe is say delta S. Through this area, if some water is flowing with a velocity v, then what is the volumetric flux of water? The volumetric flux of water is given by V into delta S. How do you get this? Volumetric flux is nothing but the rate of flow of liquid, that's all. So volumetric rate of flow of liquid through this cross-sectional area is volumetric flux. That is the volume of water which passes through this area in unit time, through unit area in unit time, that is called as volumetric flux. So how do you do that? Rate of flow of liquid through this cross-sectional area, that is amount of volume of water through this area divided by the time taken. Let us say this water flowing through this cross-sectional area covers a length of say delta L. Till here it travels in time delta T. Then of course the velocity can be given by V is equal to delta L by delta T, distance travelled by the time taken. Now velocity you know, area you know. Now how do you get the rate of flow of water? That is volume by time taken. Volume of water divided by time taken through this area. So what is the volume? I'll put it as delta V by delta T. What is delta V? Delta V is the volume, that is length into cross-sectional area, delta S into delta L. Let me write it here. Delta S into delta L divided by delta T. What is delta L by delta T? That is nothing but distance travelled divided by time taken, which is velocity. So delta L by delta T is velocity, delta S is the distance area of the cross-sectional surface here. Now that is V into delta S. Now what if this area of cross-section is not exactly perpendicular to the water flow? If I want the flux through an area which is slightly tilted with respect to the water flow, then we get V delta S cos theta. So cos theta is another factor which tells you that theta is the angle from normal to the cross-sectional area to the direction of flow of water. So that is water flux, the volumetric flux of liquid flowing through a pipe. So whereas here we have electric flux, something similar to that. That is, by definition, electric flux is nothing but the total number of electric field lines passing through a cross-sectional area, a surface area perpendicular to it. That is, number of field lines passing normal to the surface. Electric flux through the given surface is given by what? The total number of electric field lines passing normal to that surface. Total number of electric field lines passing normal to that surface. Well, let us now consider some examples here. Just like I took here some cross-sectional area and water flowing through that, let me just take here now some electric field. Say there is some uniform electric field here. And I'll consider some area perpendicular to this surface, perpendicular to this electric field. Say This is that area perpendicular to the surface. Now tell me, how many lines of passing through this? Through this area, normal to it, I have taken the surface area to be exactly perpendicular to the board, which is actually perpendicular to the direction of electric field here. Electric field strength is E, let us say. Now, perpendicular to the area, number of field lines which are passing is 1, 2, 3. So, the flux is the count of lines passing through the given surface normal to it by definition. So, normal to it, there are 3 field lines here. So, by this you can say, if I increase the strength of the field, say for example, E is the strength here already. Now I will try to increase the strength of the field. What will happen? Say, how to increase the strength of the field? You know it. By increasing the density of field lines, right? We represent strength of the field in the form of density of lines here. So more crowded the lines are, more stronger is the electric field. You know that. So now the strong field is stronger. Now before this, there were 3 lines passing through this given surface area, normal to it. Now how many are there? 1, 2, 3, 4, 5. 5 lines are there. So what did you understand from this? It's very clear. As I increased the density, the flux through this surface also increased. It means I increased the electric field strength by increasing the density of lines here, which increased the flux through the surface. So thereby I can in short say, this electric flux phi is directly proportional to the strength of the electric field. More the strength of the electric field is, more is the electric flux passing through that surface. That's simple. Now, is there any other way of increasing the flux? Yes, there is. Say for example, same field now. How many field lines are there? 1, 2, 3, 4, 5. 5 electric field lines are passing through the surface normal to it. Now, in case if I consider another area which is bigger than this, so I increase the area of the surface now, then now count the lines 1, 2, 3, 4, 5, 6, 7. I did not change the field strength, whereas I just changed the area of the surface. I increased the area, number of field lines passing through it also increased. Now what did you understand from this? More the area is, if I take A as the area, more the area is, more is the flux through it. So the flux is directly proportional to area. This is, in general, electric flux is directly proportional to both the electric field strength and surface of the area. So then, in case if the given surface, like in the previous case, I said if the water is not, if the water is flowing and the area of cross section is not exactly perpendicular to the water flow, then what will happen? That cos theta factor we took, right? Now similarly here, what will be the flux through this surface if the surface is slightly tilted? It is not exactly perpendicular to the field. Then what will happen? So let me just take another diagram for that. Say the surface here is this. Then normal to this surface, I will represent it by some n vector, normal to the surface. This n vector can also be called area vector. This is a area vector. For any surface, a normal drawn to it in that direction, we can have something called area vector. Area vector is a direction. It is a projection of area in a particular direction, which is given by area vector. Now, area vector has 2 possibilities. One is in this direction, of course, one opposite to that. So, whenever you consider a surface, normal can have 2 directions, right? Either this way or that way. So, on either direction, there is a normal. So, therefore, the area vector also has 2 directions possible for a surface. Area vector is always perpendicular to the surface, but it has 2 directions opposite to each other. So, whereas for our convention, we have very simple situation here. That is, if you have a closed surface, any closed surface, like even this duster is a closed surface actually. So now, at any point on this surface, the area vector is outward only, normal outward. So that's the area vector, not inward, it is outward. For convention, we take area vector as a direction perpendicular to the surface, outward, not inward. Okay, anyways, let me just come back to that later. Now this n cap is a area vector. Now here, if I take some electric field through this surface area, but not exactly normal to the surface, slightly tilted, say in this direction. If this is the electric field, so then what will happen? Say normal to the area makes an angle theta with the electric field. So then this electric field has two components along the normal E cos theta, then perpendicular to that we have E sin theta. Now which field lines should I count? I mean, as many field lines pass through the surface, all the E field lines will not count for the electric flux. By definition it is only the normal field lines. So every field line here has a component E cos theta which is normal and E sin theta which is parallel to the surface. Now which one will contribute to the electric flux? Only normal component. So we have to count only normal components of the electric field. So E cos theta is the one which contributes to the electric flux. So thereby we understand that phi is proportional to E cos theta. So I mean to say, in case you may be thinking it was just E, why it became cos theta now? So here also you can say this equation is applicable, because in this case normal to the surface and electric field are in the same direction. Therefore theta is 0, cos 0 will be 1. In this case normal to the surface and electric field are not exactly in the same direction. Theta is non-zero, then thereby you can understand that this value is different. So phi is actually proportional to E cos theta and directly proportional to area also. So put together we can say phi is equal to E A cos theta. Now this can also be written as, of course, E A cos theta, and remember that phi is a scalar quantity. It is a scalar quantity, whereas electric field is a vector quantity. So now if I take this as a vector quantity, A cos theta, E into A cos theta, I can put it as E dot A, where I am converting A to A vector. So that is area vector we can call. A cos theta is the area vector here. So this is the electric flux through any surface area. Now what is the SI unit for this? That's easy. Electric field. Electric field is Newton per Coulomb. Area is meter square. So SI unit is Newton per Coulomb meter square. So Newton meter square per Coulomb. This is the SI unit of electric flux. Now this is for a simple plane surface we took. But do you think practically always we will have only plane surface? No. You will have our irregular kind of surfaces. I mean, even this duster, for example, curved surface also is there here. Now, how do you find the flux through any other irregular shaped surface? Let us just check that. I'll remove this. In case if I have a surface something like this. Now on this, how do you find this flux now? What is the electric flux through this surface? Now to find that, as the surface is not exactly plane, we can imagine this irregular shape to be made of, this irregular shaped surface to be made of very tiny plane surfaces. So infinitesimally small plane surfaces constitute a full surface here. I mean, you can take this one small surface here, which is actually a plane surface, very tiny surface on the irregular body, to be a plane surface, and that plane surface has the area say delta S. Now the electric flux through that delta S small area is delta phi. Now what is the flux? Flux here is given by EA cos theta. Now here, if there is a normal and if there is some electric field E, then what is the flux given by? Delta phi is equal to electric field to normal angle is theta. So E into delta S cos theta is the electric flux, which is nothing but E dot delta S is the flux through that small surface area. Now what is the flux through the whole surface? Then that will be, you will have to consider number of these tiny surfaces, tiny plane surfaces, and find the flux through each surface, then add up all those flux values to get the total flux. That will be the total flux phi, which is equal to sum of all these small fluxes, that is delta phi 1 plus delta phi 2 plus delta phi 3, etc., which will be nothing but summation delta phi, which is nothing but summation E dot delta S. So this is the flux delta phi. And the SI unit is of course Newton meter square per coulomb. So for any irregular shaped body also you can find the flux using similar equation. Whereas of course remember this summation may turn out to be an integration in some of the cases. Of course we are going to see more about electric flux in the coming sessions. So that's about electric flux. So what is the definition? Let me just repeat it once again. Electric flux through any surface is the total number of electric field lines passing normal to that surface. So how many field lines are passing normal to a given surface gives you the flux through it. That's all. So that is electric flux. I'll remove this. Now let us see what is an electric dipole. What is an electric dipole? As the name itself says, dipole means two poles. Like magnetic dipole, you know, north and south two poles will be there. That's why it is called as a magnetic dipole. Similarly, electric dipole, in electricity, in electric charges you have learned there are two kinds of charges, positive, negative. So if both the charges are present in a system separated by a small distance, then it is called a dipole, simple. There are many such molecules which are dipoles. Let us just check in the basic definition for electric dipole first. So by definition, two tiny charges, 2-point charges, say plus Q and minus Q, 2-point charges separated by a very small distance constitutes an electric dipole. So intermolecular distances, you know, very, very tiny, very, very small distances. So as the charge itself is invisible, you know, it's so small, the distance between the two charges has to be very, very small. So when the distance between those two charges is very, very small, then it is called a dipole. Of course, if the distance is very large, then they are individual charges, isolated. They don't have effect on each other then. So when they are put together, very small distance between each of them, then it is called an electric dipole. The line joining them, the line passing through them is called the dipole axis, and center of the dipole O here. Then this is the length of the dipole length. Then the axis perpendicular to the line joining the two charges is called equatorial line. Equatorial line. So then, when I say the distance between the two charges is small, it is with respect to the region in consideration. I mean to say, this body, this is a dipole. If you want to find the electric field of this, at some point, say at some point P, if you want to find the electric field, if the distance from the dipole to the given point, that is center of the dipole to the given point, is very large compared to the distance between the two charges, let me just call it as A and A from center to each charge, which gives you 2A as the dipole length. Length is 2A now here. Now, if this 2A is very much small compared to this distance R, if R is very much large compared to 2A, then you will have some non-zero electric field, zero electric field at point P. Why is that? When the point is very far, the two charges appear to be a single body. Positive charge nullifies the negative charge, and thereby the total charge is zero. Hence, the electric field at P will be zero. So, as you go away and away, when the distance is very much large compared to the dipole length, then the electric field is almost 0. If the distance is not large enough, if it is comparable to 2a, so then electric field is non-zero. So thereby electric field of a dipole can be found in the nearby, which is in the vicinity of the dipole, which will be non-zero. If you go very much away, it is 0. Now how to find the electric field? Of course, by vector addition. That is, find the field due to plus q, find the electric field due to minus q at any point, and add the two fields vectorially, get the resultant. That's very simple. Now two possible simple cases are there. One is electric field at any point on the equatorial line and electric field at any point on the axial line. Both we are going to understand in the coming topics. Whereas with respect to a dipole, there is one more important characteristic that is called dipole moment P. Dipole moment P. So this P, dipole moment, is defined as the product of one of the charges in the dipole and the distance between the two charges, that is dipole length. Product of the magnitudes of one of the charges and the dipole length gives the dipole moment. Dipole moment is equal to 2q into a, that is q into 2a or 2q into a, whatever, q into 2a, which is 2qa. Then what is the direction? I put a vector sign here. The direction is negative to positive. So there is direction which is unit vector, I will show here. It is negative to positive. So dipole moment is always in the direction negative to positive. So in the coming session we are going to understand more about dipoles, and also we will find out electric fields at different points on the due to the dipole. So that's all for today. Thank you very much.